All right, in this lecture, we will continue from where we finished about the Fisher scoring. Fisher scoring algorithm. So basically, a recap of this is it's the Newton-Raphson with the Hessian. Let me try to move this up. With Hessian replaced by its expectation, basically, by its expectation. And actually, we know that the expectation of minus Hessian or negative sign of multiply to Hessian is called Fisher information. That's the Fisher information matrix. Okay, that's Fisher scoring. And now if we apply Fisher scoring to the maximize log likelihood of exponential family GLM. If we do that, then what we get is the algorithm called IRLS, iterative rate-weighted least square. And this is what we derived last lecture. So specifically, each iteration in Fisher scoring, which should be the beta vector value we want to find, right? The vector is the coefficient vector. We want to find the value that maximizes the log likelihood of this exponential family GLM. And the Fisher scoring will tell us it is equal to the current kth value of beta plus the inverse of the Fisher information, which is a P by P matrix at the current value of beta k, not k plus 1, beta k. I take the inverse times the gradient of the log likelihood. And that is actually what we call the score function. So we call the score function at beta k. So please note that this is P by P, and the score function as a gradient is P by 1. And of course, beta k is P by 1, beta k plus 1 is P by 1. So the dimensions are matched. And so the question to solve this Fisher scoring is to compute the score function and the Fisher information matrix. So we need to compute both. And in our last lecture, after the derivation, we found that we can write it in the form of reweighted least square. So essentially, we can show that this beta k plus 1 can be expressed as the inverse of X transpose times the W matrix we define, given the current parameter values. So we write WK. And the design matrix X is fixed, so it doesn't update. Times X inverse times X transpose times WK times a vector. And for the vector, we give it a notation. We write y minus mu times d eta d mu. So this is the whole thing at the kth value. So that's what we have. And to further solve this, right, our goal is to solve for beta k plus 1. What we can do is that we can multiply this X transpose WKX to each term. So then we don't have the inverse in the last term, but we have X transpose WKX with beta k plus 1 and beta k left multiplied to each of them. Then we can combine the terms. To combine these terms, XWK with this X transpose WK, X transpose WK here, X transpose WK here, we can merge the two terms. So that will give me a simplified form. So essentially, we can actually rewrite this as beta k plus 1 equals to X transpose WK X inverse. So we multiply the 1 on the left of that to the right-hand side after merging these two terms times X transpose WK, and we have a term created called ZK. It's a vector. And here where zk is essentially defined as x times beta k plus this thing, y minus mu d eta d mu at the kth value. That's what we have. So this is what we call as the working dependent variables in place for our actual response y. And this is a vector n by 1. So this vector is going to replace our original response vector y, which is also n by 1. So essentially, you see that we are doing this weighted least square or weighted linear regression in the kth iteration. So what we are doing in each iteration is that we use the current value of beta to update zk, to update wk, and then we continue from there. So that's why in each iteration, we're just doing weighted least square. And that will make this computation feasible in the old days where we don't have powerful computers. Otherwise, nowadays, if you have the form for the log likelihood, you could use a brute force to directly maximize it, right? With powerful computers, you can do that in a numerical way. But this old way, iterative reweighted least square, provides some very nice intuition and some nice result we can use to help us talk about the uncertainty of our beta estimate. So suppose that, like in our linear model, if we can have beta hat as the MLE that maximizes, which is the argmax of this log likelihood of beta. Suppose that we have this, and we want to talk about what is the covariance matrix of the beta hat, so we know the uncertainty of our estimates. If we want to talk about that, then I think this iterative reweighted least square can provide some useful insights for answering that question. Okay, so last time we also said this working dependent variable zk can be interpreted as a Taylor expansion, an approximation of g of y. So the thing is that we actually have this. So x times beta k, right? We know this is called what? Just a few more steps to help you remember. We call that eta k. Okay, so this is the linear predictor. Eta k is n by 1. And we also have for each response, g of mu I, the expected value of yi is called mu I. G of mu I is known as eta I, right? So if we put k here, we put here. That's how we are going to go back from eta ik to mu ik. And you see, essentially, G, the link function, maps the expectation of our response to the linear predictor, right? That's what it does. And if we look at here, essentially, this is eta I. This is zi is like eta I. It's like linear predictor space. But we also add this part. And this part, if you look at it, is essentially, so for this long format here, the ith component, let me just write it one more step, y minus mu d eta d mu k, right? The ith component, let me just put it here, is essentially yi minus mu ik times the derivative of the link function at mu ik. This is what it is. So essentially, you see, this is like we are, so putting this together, we are like zik equals to g of mu ik plus yi minus mu ik times g prime mu ik. Okay? And this is the first order Taylor expansion of G of yi. That's what we have. So essentially, we're doing this Taylor expansion to create a working dependent variable which approximates transformed response I, G of yi. And that's for this working dependent variable, the new response in each iteration. The WK serves the purpose as in weighted least square. Basically, the weight for each response is 1 over the response variance. So essentially, WK is a diagonal matrix, right? So WIK, which is the ith diagonal for the W matrix, is essentially 1 over the variance of ZIK. But as the variance itself involves parameters, we need to put K on top of variance to mean that the variance calculation depends on the current parameters. So all dots connected together, this is weighted least square in the kth iteration. Okay, so any questions regarding what we did here? I would say the biggest, how to say, trick, or you can say the core for this whole IRLS algorithm is the construction of this WK matrix and the working dependent variable. As long as you construct them based on the Fisher scoring iteration, what is the score function, what is the Fisher information, you derive those, and then you combine terms to create this form, that's where you get it. And so last time we also talked about how to actually implement, do some hand derivation of the IRLS using under the individual data logistic regression and group data logistic regression. That's what we did on the board last time. All right, so now suppose that using this RLS algorithm, we are able to achieve this MLE. Okay, suppose that beta hat MLE is already obtainable. Then we want to ask some follow-up questions before we talk about the inference of beta hat, because we haven't been there. So this is something we will talk briefly later. But before we talk about the inference, let's first talk about a very important question, which is whether the GLM, exponential family GLM, is a reasonable model. Okay, this is like a model selection problem we always need to ask. Okay, so let's say that we have exponential family GLM with parameter estimated as MLE beta hat. So this is what we call a fitted model, because beta hat MLE is estimated from data. So we hope that this model can fit well to our data. But the question we want to ask is the model fitted well enough? Okay, how can we answer this question? And to answer this question, it is commonly called as goodness of fit test. And we can do this, we can ask this question for almost every model. So as long as we're making a model assumption, which is the model is what? It's about our assumptions on the relationships of the variables. That's the model. And we are making the systematic structure to link our predictors to the expected response. And then we use the random structure as an assumption of how the response will be distributed around its expectation, right? That's a two-layer. Then the question is whether this is a reasonable model. And good as a fit is about how well the model fits to data. So now let's ask you this question. What is the model that fits perfectly to the data? So there's no discrepancy between the model and the data. So I can let you think maybe for 10 seconds and I can give you the answer unless you want to voluntarily speak up. So what model fits perfectly to the data? And that's what we call saturated model. So you will see this term also in the statistical literature. So when we say saturated model, we actually mean that the number of model parameters equals the number of observations. That's what we mean. So essentially, you maximize the complexity of your model, so it's equal to the number of observations. So this may no longer be the case in the current stage of those large language models or deep learning models, because now the number of parameters is huge, right? But whether the number of parameters is equal to the number of data points, big data, I'm not sure. I think it depends on the context. For certain applications, maybe not, but for certain applications, yes. Here, we're talking about the sense where we still can interpret the model parameters. So we know what each parameter means. So in this case, the number of model parameters, when it's equal to number of observations, we know the model can perfectly describe our data. So in this case, in the GLM case, what is a saturated version of the model? So we basically go back to the two-layer structure, random structure. So we will basically say that yi response independently follows its own distribution. And in our case, it's an exponential family distribution, right? And we can just say that it's mu I with some parameter phi. So please note that in our old way of writing the model, we use theta I. So there is a one-to-one relationship between mu I and theta I. And we know actually that. We know that it's actually mu I is b prime theta I, right? That's what we know. And depending on what the Bayes function is. So that's the random structure. For the systematic structure, that's the key. In GLM, we assume G of mu I, transformed mu I, is a linear combination of predictors. We write xi transpose beta. And the key thing to pay attention to is that beta is shared by all i's. So beta is not specific to the ith observation, but it's a common effect coefficient vector. However, and also we know that the dimension of beta, right? Beta being commonly p-dimensional, in the classical setting, p is less than n. So we have fewer predictors than our observations. However, in undersaturated model, we want to give the maximum flexibility to those mu i's, because mu i's, mu1 to mu n are our key parameters. So give them the maximum flexibility. What do? We just don't constrain them. We don't try to link them into the predictors to explain each of them. We just let them vary freely. So basically, under the saturated model, unlike the GLM, we just keep mu1 to mu n unrelated. We don't try to assume a common relationship among them. So in other words, you don't need to use your predictors at all. You just try to estimate mu1 to mu n based on y1 to ym. And then what is your estimate then? Each mu I is its own parameter. You just have one observation about it. That's yi. So in this case, you can obviously see that, right? Because each parameter has its own observation. Then the most obvious or natural parameter estimate would be mu1 hat is estimated as y1 to mu n hat estimated as ym. That would be our estimates under the saturated model. Okay, so this will be the saturated model I call that mu SAT to mean saturated. Well, for GLM, we already know we have the mu hat GLM from the MLE. What is that? Each mu I would be based on the linear predictor and transform it back, right? So I just write here. So mu I hat GLM is actually the inverse of the link function of is the inverse of the link function of the linear predictor eta I. And eta I hat is xi transpose beta hat. That's it. So once we get a beta hat, we multiply it to the predictor inner product, and that gave me the eta I hat, which is the linear predictor, and then I map it back to mu I using the inverse of the link function. That's my mu I hat GLM. So essentially, if we talk about the degrees of freedom, mu hat GLM has degrees of freedom of p because we have p parameters in beta hat, while the degrees of freedom of mu hat saturated is n, since each parameter estimate can vary freely. Does that make sense? So the two models have different degrees of freedom. So motivated by this, to assess whether the GLM fits the data well enough, we are comparing GLM to saturated model. In the sense of what? How do we say a model fits data well? Likelihood. The reason we can use likelihood is because they share the same random structure. And the random structure determines the likelihood function form, right? How the data probability density or join probability is depends on the parameter value. So both models just change the parameter values, beta, but they have the same random structure. So therefore, we can compare their maximum likelihoods to say, oh, by maximizing the GLM parameter and not likelihood, and also by of course saturated model, this is the MLE. No constraint on mu i's, the MLE would be yi as mu I hat. So we compare the maximum likelihoods under the two models to see whether their differences is something meaningful or something too big to say, yes, GLM doesn't fit data as well as the saturated model that does. That's the rationale. Does that make sense? So essentially, what we're trying to do is to compare the likelihood or log likelihood. I think because they're monotone, it doesn't matter. We're comparing the likelihood of mu hat GLM versus the likelihood of mu hat unsaturated model. That's what we're doing. And the two likelihoods will be written out in the same way as they share the same random structure. All right, how do we measure their discrepancy? We think about likelihood ratio test statistic. All right, so essentially, we give this a name. We call it deviance. You often see this term deviance in the literature context of GLM. So deviance is defined as the likelihood ratio test statistic, LRT statistic of GLM versus the saturated model. Because in this case, we can consider the two models as nested as well. Because GLM is a more constrained model, it constrains the mu i's, mu1 to mu n. They are constrained to follow the same systematic structure, while saturated model doesn't have the constraint. So it's a more complex, more free model. So in this case, the deviance, right, recall, or the likelihood statistics defined as what? It's defined as 2 times the log of likelihood ratio is the log of the maximum likelihood of the smaller model. And the smaller model is the mu hat GLM over the maximum of the likelihood under the saturated model, mu hat saturated. Maybe I should get rid of the max because using mu hat for each, the likelihood has been maximized already. That's it. So then if you want to simplify this a little bit, it's actually 2 times log likelihood at mu hat saturated model minus log likelihood at mu hat GLM. That's it. Okay, so you can also tell the direction for the subtraction based on what? Based on which log likelihood is bigger, larger, since you know the deviance or log likelihood test statistic cannot be negative, so it must be non-negative. And the saturated model has more parameters, it can fit the data better, and you can expect a larger likelihood. So saturated model will have a larger log likelihood than the GLM. So therefore, you know the difference won't be negative. But you hope that the difference is not too big. Okay, so some specific examples I can tell you. So for logistic regression, we can write the specific forms for deviance. Let's say logistic regression with group data. Okay. Recall for this model, the random structure is yi independently following binomial with the group size ni and the probability of taking one as pi I. Okay. So in this case, mu I is ni times pi I, right? That's what we have. So we have derived the log likelihood when we give an example of IRLS last time. So I won't repeat that, but just say that in this case, the deviance, D, will take the form as 2 times the sum of observations I from 1 to n. In the sum, we have yi times log yi minus plus ni minus yi times log ni minus yi. This is actually what? This is from the saturated model log likelihood because we are using yi as mu I hat. That's why. Minus the log likelihood of GLM. We have yi times log mu I hat. And this mu I hat is from GLM plus ni minus mu I hat times log ni minus mu I hat. That's all. That's it. So essentially, I'm having the difference. The first part comes from the saturated model. The second half comes from the GLM. And that's how we calculate the deviance. And then how can we say whether the deviance is too big to let us conclude that GLM is significantly different from saturated model, so it doesn't fit our data well enough? We use likelihood statistic, deviance, and its asymptotic distribution to guide us. So you know that under asymptotic distribution or null distribution of this D, it is when the two models fit the same data equally well, and their difference is only due to randomness in the data. That because for different data set, you will observe a different D, right? It's due to the randomness in the data. So essentially, we write that D under the null, that is the two models, GLM is equal to saturated model. Under this should follow a chi-square distribution, where the distribution's degrees of freedom. Degree of freedom is the difference of the two models' degrees of freedom, and that's n minus p. Okay, so essentially, the smaller the model for GLM, or the bigger difference that the two models' complexity is. That means the simpler model is much simpler than the saturated model. So you will have a bigger n minus p. And that will give you a more spread out chi-square distribution, because we know for chi-square distribution, its mean is just n minus p. It's just its degrees of freedom. Its variance is 2 times the degrees of freedom. So the larger the degrees of freedom, the more spread out the distribution is. It means that then you can expect a larger d value, even the two models are fitting data equally well. So essentially, this gives us a way, the null distribution gives us a, baseline to calibrate the value we observe for this d, whether it's too big compared to that. So that's it. That's basically what we are doing, here. Yeah. But to know that, one thing we cannot do, essentially, is if you are using individual data, not group data, then this idea wouldn't actually apply. The problem there is if you have ni equals 1, okay, if you have ni equals 1 and yi is binary, then you will have a log 0 issue because your saturated model just is not well defined. So you will have a problem there. So this deviance approach only works for logistic regression with group data. So basically, in that case, your saturated model's mu I hat estimate can be well defined between 0 and 1. That's it. Okay. This is one approach to assess this. So essentially, how do we say the deviance is too big? Too big to be, to say that, oh, the goodness of fit has failed, or how can we convert this to a p-value? We basically take the right tail probability of this null distribution. Okay, so essentially, suppose that the d, we observe d, let's call it small d. Okay, then the p-value is defined as the probability under this null hypothesis that big D is greater or equal than small d. So this is the right tail of chi-square n minus p distribution. That's it. So deviance is the most widely used statistic for assessing goodness of fit. It's basically likelihood ratio test. And the second one was proposed by Carl Pearson, who is also known for the Pearson correlation. So he has, because he's one of the pioneers of statistics, he has invented many things that we're still using today. So for this problem, his statistics called Pearson's chi-square statistic. And Pearson's chi-square statistic has a general definition, which is I just call chi-square, and now you write big P to mean Pearson. But don't confuse this with the chi-square distribution. This is a chi-square statistic. We just follow the convention to write in that way. So the general definition is what you might have seen with the so basically the contingency table to test whether two variables are independent. So I think you have seen that already. That's a famous example. So suppose that I have two variables. So basically variable 1 and 2. Sorry, variable 1 takes two values, 1 and 2, and variable 2 takes two values, 1 and 2, or binary values. So I just count how many observations have 1 and 1 in the two variables. That's number A. And number B observations has variable 1 with value 1, variable 2 with value 2. So I just fill out this table, right? So categorization. And then I can use this table to ask a question, are the two variables independent or not? And this problem can also be solved with the Fisher's exact test. So this is a very classical problem here. And Pearson chi-square statistic can be used to address this problem and also what we have over there. So essentially, this can be said as a sum. So if we have multiple categories and we sum over categories, all categories, and for each category K, we would compare the value or the count we observed in that category, we call it observed K, minus expected value of that category under our null hypothesis, under our assumption, like variable 1 and 2, variable 2 are independent, that's expected. Take the square of it and normalize that by expected value under category K. So this is the general definition of Pearson's chi-square statistic. Okay, so in this case, if we apply it to the grouped logistic regression data, so then each group I is one category. And in this category, our observed count or observed value for our response is yi. Our expected value for the response is our mu I hat from the GLM. And furthermore, don't forget that for group I, we also have the other side as the other category. That is, we have the number of ones, we have the number of zeros. So Ni minus Yi is the number of zeros in group I. So together, apply that to the group data. So it's like logistic regression with group data. For that, chi-square P can be written as a sum of my groups, I from 1 to n. In the group, I look at the number of ones. That's yi minus mu I hat. So mu I hat is expected number of ones over mu I versus plus the other side, which is Ni minus Yi, that's number of zeros, minus Ni minus mu I hat, right, square, over Ni minus mu I hat. That's it. So that's the Pearson's chi-square statistic for logistic regression. And you can combine the terms. Okay, by combining the terms, the two terms in the sum, essentially you'll get I from 1 to n, Ni, Yi minus mu I hat square, mu I hat times Ni minus mu I hat. Okay, that's it. So for this one, right, so essentially, you can do the calculation. And this doesn't have that log 1 equals, log 0 equals negative infinity issue. So this formula can still be applied to individual data. So you don't have that issue at all. As long as you don't have, say, mu I hat being exactly 1 or 0, that is a problem when you run logistic regression, when your two classes, say 1 and 0, are perfectly separated. So that's something we need to pay attention to in practice for logistic regression. So when that happens, it means that you can perfectly predict a observation to be 1 or 0, and you would have some infinity issue in the parameter value convergence. So this is something when people, when they use the MLE to fit logistic regression, it seems to be quite counterintuitive, because if the data are perfectly separated, let me just draw it here. Suppose that this is variable predictor 1, predictor 2. I have two predictors, and I have zeros here. I have ones here. So the data can be perfectly separated by a linear boundary in X1 and X2 space, in the X space. So you can try it, and you can find that Essentially, when you have the linear boundary to do the perfect separation and you convert it back to the mu I, you will get perfect 0 or 1 mu I hat. And that will create a problem there. Because if you think about what is mu I hat, or if we think about it as, or pi I, let's just call pi I, which is mu I hat over ni, okay? So essentially, it is exponential function to xi transpose beta hat plus 1 plus exponential function x transpose beta hat. If you have pi I hat exactly 0, exponential function 0, it means what? The exponential function cannot be exactly 0. If it is, then the beta has to give you some infinity, negative infinity value in the inner product, and that will be a problem. So you have some convergence issue there. So people realize this problem, and then an alternative approach which has been popular in machine learning, which was support vector machine. So support vector machine actually dominated machine learning for doing classification for years until neural network researched due to the big data availability and GPU computation, right? But before that, support vector machine was known to be very powerful because when your data are perfectly separated, you can have multiple lines that can separate them. Which line would you pick? Then support vector machine will pick the line that has the largest margin to separate data points. Okay, so that's just an overstretch from our discussion of logistic regression. Again, I want to say that the idea of doing this goodness of fit test is very general. What it tries to answer is the fact whether you can, is trying to answer the question whether you think the model fits data well enough so you are happy with the model or you choose the model. Because you don't want to choose a model that is interpretable but fits data too poorly because that may not be meaningful. Oh, finally, I want to say this Pearson's chi-square statistic. How do we use it? The good news is that you can also use the chi-square distribution with n minus p degrees of freedom under the null hypothesis. And this is also an asymptotic result. So you can also use it to help you decide whether the Pearson's chi-square statistic is too big, looking at the right tail probability under the null distribution to say whether you think the goodness of fit is good enough. If it's too big, then it's not good. So smaller p-value means poorer goodness of fit test. Okay, any questions about this part? So this is our discussion about whether the model fits well enough. And we talk about the deviance, which is the deviance between the saturated model and which is the likelihood test statistic between the saturated model and the GLM. And GLM in this case is the smaller model. And don't confuse this with what we said about the ANOVA. So in linear model ANOVA, the smaller model is what? Is the intercept only model, the baseline model without predictors. And then you add a predictor, and that is the more free model. And then you add another predictor, you get another bigger model. So you need to be clear about the nesting structure of these models. So when you do the likelihood test to compare two models, what are they and what do they mean? So to compare a linear model or generalized linear model with a baseline model without predictors, we are trying to answer the question whether this predictor is effective, whether it's useful. But to compare a GLM with all your predictors, the predictors you decide to include versus the saturated model, you're answering a different question. That is the model good enough? Does the model describe my data well enough? Okay, any questions? If there's no question, let's move on to another topic. So suppose that
assistant appointment弄
I'm sorry.
Oh.
Okay, I don't think it's related to the class. All right. The second question is, suppose your model passed the goodness of fit test, so you conclude that the model fits data reasonably well. Okay, then the next question is, how do we interpret the model? So this is what we call inference of beta. That is, you like the model, so then you want to make a story out of the parameter. But you don't know the true parameter value. You only know the parameter estimate. Then what do? Right? So this is what we do. So now the IRLS will be used. So suppose that we have the convergence, right? Iteration. So from the IRLS, upon convergence. So when we say convergence, everything stabilized, including W matrix, including your working dependent variable. So both the W and Z will not change. And that's where you stop. So in the last iteration, we can just write as beta hat because that's also the value we stop as X transpose WX inverse X transpose WZ. So essentially, you are stopped at where the solution is just a weighted least square solution. So you can also think about this working dependent variable as where it very well mimics the g of y. Basically, that's what it is. So you stop at a very linear region of your likelihood function, and then you just get a solution there. So the last step there is like weighted least square. And this provides a basis for our inference of beta. So essentially, if you think about this formula, let me ask you one question. Beta hat is a random? Now the answer should be obvious, right? After so many lectures, is beta hat a random thing, but random quantity, random vector? No. Why isn't it random? Actually, it is random because it's our parameter estimate. It's based on our data. If we think about our data as random, then beta hat is random because we get a different data set, we get a different beta hat. Then where does the randomness of beta hat come from? In this formula, the last steps iteration in our IRLS. It is from Z because Z is our transformed version of the response of our Y, and Y is the random variable. W is a random. Actually, no, because W is depending on the parameters. If we believe that we know the true parameters, then we don't know, we don't need to worry about W. So essentially, if you know the true parameters, let me just clarify this a little bit. If we know true model parameters in the GLM, W is known. So only Z is random. So in that case, if we calculate the variance covariance matrix of beta hat, it's just based on this Z. So we will just treat this whole thing, the series of matrix in product before Z as a matrix left multiplied to Z. So essentially, we know the formula for that calculation. So essentially, if I call this matrix as A, okay, A times Z, it's just A times the variance covariance matrix of Z times A transpose. That's the formula. And we know this Z is P by N, okay? Z is N by 1, so its covariance matrix is N by M, and Z transpose is N by P. So then my covariance matrix for beta hat will be P by P. Okay, then put A back in. We can see that we first need to get the covariance matrix of Z. What is that? We know that already. Remember our definition of the W matrix. Each is a diagonal matrix, and the ith entry of W is just 1 over the variance of Zi, right? That's what we have. So therefore, we know the variance of Z is just W inverse. That's it. So essentially, we have A times W inverse times A transpose. Okay. And we put A back in. So you can see
Jessica,
you have, sorry.
I'm
Can
a
I
little,
finish this first
yeah,
and
sure.
yeah. So W inverse here, and then we put this transpose back, W times W, because W is diagonal matrix, it's transpose itself, X times X transpose W, X inverse. So then we can see that we can cancel out one W here, and we can have X transpose WX in the middle. That can be canceled with this former one or the latter one. We just keep one copy of X transpose X inverse. That's it. Yeah, your question.
Yeah, I'm slightly confused about why we're saying that W isn't random if we're substituting in W for a quantity involving Z, which we just said was random.
No, W involves only variance of Z. It's not about Z. It's about the variance of Z. And the variance of Z is determined by the model parameters. As you know the model parameters, you know the variance, and the variance is not random.
Okay.
Yeah, yeah. So this is under the assumption that W, the model parameters are known. So W is known, so not random. Okay, so therefore you see variance of beta hat is this quantity X transpose WX inverse, not random. But in reality, that's my next step. In reality, we don't know model parameters, we don't know W. So what do we do? And this is a technique used in statistics throughout. It's known as plug-in. So for plug-in, it means that we just try to replace parameters we don't know by their estimates. So in this case, we call the plug-in version of the covariance matrix as variance hat. In this version, we replace W by W hat. That's it. So this is what we used a lot in statistical inference. Essentially, we first try to derive the variance assuming parameters are being known, and then we replace the parameters in the variance formula by their estimates. Okay, so this can easily get into a infinite loop of randomness. So you may say, yes, this variance formula is not random, but when you do a plug-in, as W hat is random, then this variance hat will become random. Do you need to consider the randomness or uncertainty of variance hat? That is a question you can ask, right? And then you can calculate that variance of this variance hat, but that variance of variance hat will involve unknown parameters again. You have to do plugin. So this is like an infinite game. And I think this will be something people can criticize this frequentist inference for, because essentially at this step, you are using variance hat, a random quantity, to represent this unknown variance beta hat. You are interested in variance beta hat, but it's not directly achievable since you don't know model parameters. So, but instead, what you're doing is that you're using your estimates for model parameters as a replacement. So basically, you still hope that W hat to be good enough, to be close to W, then this variance hat is close to variance. And then you can say something about the beta hat. But you are also thinking, yeah, beta hat is not perfect. So that's why I care about its variance. But I hope W hat, which depends on beta hat, to be good enough, so I don't need to worry about its difference from W. So there is something there. I don't know, I don't want to get into too detailed or too tricky for you guys, but I want you to realize that inference is not perfect. We're making assumptions here. Especially when we do this plugin, we're assuming that the estimate is not too bad. Otherwise, everything breaks down. I hope that makes sense to you. Yeah, but you may say, oh, I don't need to worry too much if my model is reasonable and if I have a very big N, like in the big data era, I have a very big N, then I can estimate this beta hat to be very well, and I have a very small variance, and then maybe I don't need to care too much. But that is something you have a lot of data. But if you have small data, you care about the variance, then you need to do this to see whether the variance is too big. So that will make you be kind of worrying or uncertain about making any viable solutions from beta hat about beta. Especially what we care the most about is whether beta J is 0 or not, right? Whether the predictor J has any effect or not. That is often the question we try to ask. Okay, yeah, so with this, then everything we told you before can be applied. So including t-test. The tests we can do. The first one, t-test. Which is the null hypothesis, beta j being 0. Okay, in this case, the t statistic would just be a normalized version of beta hat j over the root of variance hat beta hat j. Essentially, you just need to grab the jth diagonal element from here, put that here, and that's what you get. Okay, so it's basically beta hat j over the square root of the jth diagonal element of this x transpose w hat x inverse. Okay. And if we don't want to be too exact, if we can use the asymptotic distribution, it's actually pretty easy. Asymptotically, we can just use the standard normal distribution as the null, as an asymptotic null. But if you want to be more exact, you can use the t distribution. But for the t distribution, recall that we have the n minus p as the degrees of freedom, because that's just what we have between the, how to say, given the model constraint, right? We add a p predictor to tie things together. So we remain n minus p degrees of freedom. So this is a t-test. And for the Wald test, second, when we want to test whether a subvector of beta is 0. So if we do that, we just write beta as two subvectors, beta 1, beta 2, with dimensions p1 and p2, such that they add up to p. Okay, so if we're doing that, and if our null hypothesis is, say, beta 2 is 0, but of course this is 0 p2 dimensional. So if that's the case, the wall statistic is just beta 2 hat times what? We need the inverse of the beta 2 hat, right? We need the very inverse of the variance of beta 2 hat. So what is it? We actually need to go back to here again. So if we just write this as a block matrix, follow in the P1, P2 dimensions, if we write it as V11, V12, V21, V22. So specifically, we have P1 here, P2 here, P1 here, P2 here. Okay, V22 is just P2 by P2. We put that here, V22 times beta 2 hat. This is a scalar. And so this wall statistic would actually follow chi-square, no, not chi-square, yes, chi-square distribution. Follow a chi-square distribution with P2 degrees of freedom. So because here we are adding P2 variables to our model, and we want to see whether they should be there. Okay, so that's the wall test. So it's just like a generalization of linear model, except that we are doing it in a how to say weighted least square way. We need to consider the weight over here. That's the only thing. Other than that, it's the same. And the third test we can do is the likelihood ratio test. So we can still answer this question. Same question. Likelihood ratio test is beta 2 useful? Are the P2 predictors useful? So in this case, what can I do? We need to get a log likelihood ratio test statistic, right? So the LRT statistic should be -2 times the log of the ratio of the maximum likelihood with beta 1 only over the maximum likelihood with the full model beta, right? So beta includes beta 2, while beta 1 doesn't. So we can actually use the deviance statistics. Suppose that if your R has the deviance function you can make use of, you can easily leverage that function to help you do the calculation. Because essentially, you can see that I can easily write it as 2 times the log likelihood of, let me just write it this way, beta hat, the maximizer under the full model, minus log likelihood under beta 1 hat, which is the MLE with the beta 1 only model for that. But what I can do is that I can introduce the saturated model into each of them. Then I can see something interesting. So I can have the L mu hat saturated model minus L beta 1 hat minus L mu hat saturated model minus L beta hat. So you can see that I can cancel out the log likelihood of a saturated model itself minus itself, and I can restore this double negative sign will give me log likelihood beta hat, and then minus sign log likelihood beta 1. So essentially, you see the first term is just my definition of deviance. It's a deviance of the beta 1 only model, beta 1 hat, minus the deviance of the bigger model with beta hat. So essentially, the smaller model will have a bigger deviance. That makes sense, right? Because it's more different from saturated model than the deviance of the bigger model. So that's why this difference will be non-negative. So I'm not saying anything special here. I'm just saying that if you already have our function for deviance calculation, you can leverage that, use it to easily do the calculation of the log likelihood test statistic. And that's it. And then for this one, under the null hypothesis that the two models are the same, or the beta 2 is not beta 2 is not useful, you don't need to include it, then this will be following a chi-square distribution under the null with the degrees of freedom difference as P2, because they differ by P2 parameters. That's it. Okay, so we covered two things. Given you fitted logistic regression or generalized linear model, one is model diagnostics or goodness of fit, whether you think the model overall is good. Second, how to do inference based on beta if you like the model. Okay, any questions? Okay, now we will talk about the third aspect, also related to diagnostics, but now it's not about the overall model fitting, goodness of fit, but it's about the residuals, that is individual data points, whether you need to care about individual data points being an outlier, and that should be excluded. Okay, so for that is when we do diagnostics on individual observations. Okay, so if we do that, then we can follow what we did with linear model again, except that for linear model, it's very straightforward, just yi minus mu I hat, right? But for the generalized linear model, it may not be that simple because for yi minus mu I hat, we also want to standardize it because we realize that if we just do this, just say it yi minus mu I hat, we realize that these EIs don't share the same variance. So that's why we can even do the standardized residual. Remember that, which is just EI over some root of the variance hat EI. Because this variance involves unknown parameter sigma. So we have to replace it by the sigma hat. Anyway, so we have this for linear model. How about GLM? So for GLM, we of course need to think about standardizing by the variance. Same thing. So for GLM, the Pearson residual is essentially standardization, nothing special. So Pearson residual, big PI. So the P stands for Pearson, is basically yi over mu I hat divided by the variance hat of yi. That's it. So we are standardizing by the variance of yi, but the variance involves unknown parameters, so we put hat. So specifically, if we again think about the logistic regression with group data, so that example, we have yi minus mu I hat, and this specific denominator would be mu I hat times ni minus mu I hat divided by ni. That's it. Yeah, it's basically the variance formula for yi, given the binomial distribution. Because binomial distribution's variance is ni times pi I times 1 minus pi I, and we're just plugging the hat. That's it. Okay, that's the Pearson's residual. And same as our rule of thumb for the standardized residual is that we compare SI to 2, right? Absolute value 2. We do the same rule of thumb here for Pearson residual. If its absolute value is greater than 2, it's probably too big. Then we don't think this observation is fitted well to the model. That's the GLM. Pearson residual. Second type of residual is based on deviance. So recall that if we show you here, deviance, this is the thing we wrote, right? Deviance 2 times the difference of 2 log likelihoods. As we know that in log likelihoods, we can have a sum over observations. The reason is because the likelihood function, if the data points observations are independent, is a product of individual observations probabilities, right? So we have the sum over observations. So if you look at the sum, inside the sum, each term is contributed by the ith data point. So we take that out and we call that the deviance residual. That's it. So essentially, the deviance residual is just the ith term in the sum of deviance. That's it. So in particular, for logistic regression with group data, the ith deviance residual is just 2 times yi log yi plus ni minus yi log ni minus yi minus yi times log mu I hat plus ni minus mu I hat times log ni minus mu. Yeah, that's it. So basically, for the logistic regression with group data, so this is, let me just write it again, logistic regression with group data. This deviance residual is just 2 times yi times log yi over mu I hat plus ni minus yi times log ni minus yi ni minus mu I hat. That's it. But something I forgot to say, is that we need to take the square root. That's it. We take the ith term in the deviance and we take the square root. What is the rationale for this? The reason is because deviance by taking the sum follows chi-square. So we're thinking about chi-square as the sum of squares of standard normals, standard Gaussian random variables. We're using that rationale here. And so therefore, we think of each term as a squared normal term. That's why we want to take a square root of it so we can compare this to some value we consider to be big for standard normal random variable. That's 2. So that's why we are comparing this square root to 2. I know it's not exact, but it's something people just use, as some rationale. So again, it's called a rule of thumb. So you compare this to 2. If it's bigger than 2, then it's too big. Okay, and I think that's all I want to say. So Pearson residual is basically generalized from the residual idea under linear model, while the deviance residual is based on the deviance concept, but we want to look at each data point's contribution to deviance. But if you want to go further from the Pearson residual, you can argue, yeah, different PIs still have different variances. Can I further standardize it? Yeah, you can go further and say that as well. So, but I think it's an approximation anyway. So we just want to look for data points which seem to be an outlier, and then we may or may not include them in our model fitting. And I think these kind of diagnostics is more important for small data, where every data point is valuable or is precious. You don't want to throw away a data points more easily. But for big data, I think we need a different practical practice, right? We may think, okay, leaving out 1 or 2 data points doesn't really matter that much. So that will depend on the data you have. Okay, so that concludes all I want to say for diagnostics for GLM. So we use IRLS to get us the beta hat, and start from there. We first do goodness of fit test to say whether we accept our model. And if we do, then we do inference of beta to say, oh, whether we can tell a story out of the model, whether a predictor J has any effect or whether a subset of my predictors have any effect. That's the inference part. But before you do the inference, you may also want to decide on outliers, whether you think your model has some obvious outliers that should be excluded. So these are the considerations we have for model construction or model building. Any questions before we wrap up this lecture? No. Yeah, because I can only tell from the people who showed up. Okay, so then I'll see you in person next Monday then. Okay, bye. Bye, everyone.
Thank you.
Bye.